So process measurement fundamentals. Now we work according to the basic set of units, the SI units. So when you talk about length or mass or current, that's the units that we will use in this module. Now if you look at the basic measurement performance terms and specification, we have things like accuracy. Okay, I just want to see something over here. Okay, so accuracy determines how precise or correct the measurement are to the actual value. So if this is the value that we try to measure, then we can have a certain systematic error or bias. On top of that, we can also have some random errors in terms of precision, and then we might also have a problem with repeatability of this measurement. So all of that makes up then the total error, the inaccuracy that we have in our measurement. So this determines then the precise or correct measurement, how that is with respect to the actual value. Now the range of operations, that's defines the high and the low operating limits between which the device will operate correctly and at which the other specifications are guaranteed. So as long as it's within that range, then the specifications for, let's say, that specific operation is then guaranteed. Now, operation outside of this range can result in things like excessive errors, equipment malfunctioning and even permanent damage or failure. So that's how important it can become depending on the type of process. Then also what we have is budget and cost. Although that's not so much a specification, the cost of the equipment is certainly a selection consideration. Even if all your other specifications are met, this can prove at the end of the day to be an inhibiting factor, especially if you're installing a new plant and you're now beyond the project time or schedule, and then the cost seems to be accumulating. Then also in terms of measurement, we have something what is called hysteresis. And that's the difference in the output for a given input when the input is increasing. So there you can see the input increasing and the output again for when the input is decreasing. So you can see they don't follow the same path. So there is a difference in that path, and that difference is what's then called the hysteresis. And then we have also linearity. That expresses the deviation from a straight line. So here we have our straight line, but our actual response deviates from that straight line, as you can see, above and below that line. So that's what we specify as linearity. Then repeatability, that defines how close a second measurement is to the first one under exactly the same operating conditions and for the same input that we have. Now, repeatability generally within the accuracy range of a device, and it's different from hysteresis, which we just looked at, in that the operating direction and conditions must be the same. For hysteresis is operating, increasing and decreasing the value. Here they are the same, and you can see how close do we get to the same value. So we have our control variable, and we have certain limits in which we wanted to operate the process variable. And then the last thing in terms of this measures is response. So if I give it a step input, how quickly will it respond to that? So as you can see, we have where we have a step response time. So how long does it take to actually now respond to the step response before it now reaches the final steady state value? And then it also takes a time, a settling time, because there might be then some overshoot depending on your control, and then eventually it will settle within that specified band. And once it's in that specified band, we say that's where up to there is where the settling time will be measured, from where it starts to where it's within that band. That's the settling time. Then just a lot of definitions in terms of terminology. Ambient is your surrounding environment, reference a particular point. Attenuation is a decrease in the signal magnitude, can be over a period of time. Calibration is comparing and determining the performance accuracy. Closed loop is where the process variable is used to calculate the controller output. Temperature coefficient resistance, that's change in electrical resistance per degree, change in temperature. Coefficient, that's a temperature coefficient, defines how much change in temperature there is for a given change in resistance. Cold junction is what's referred to a thermocouple junction, which is also known as the reference temperature. Then we have compensation, supplementary device used to correct errors due to variations in your operating condition. So that's, you have to compensate for that. Controller is that what will regulate the control of the process with the control variable. Elastic, that's the ability of the object to regain the original shape. Excitation is the energy supplied required to power a device for intended operation. Gain is the change of output to change in applied input. And there can be no unit, but if we look at your welcome, Jason, I couldn't find your link, only my link, because Jason asked me if I can find the link. Normally I get an email with both links, but my email only had my link. So welcome, we've just looked at the initial few slides, and we're looking now at terminology. Then hunting is undesirable oscillation at or near that required set point. So it actually hunts for that set point, but it's now oscillating at a higher and lower value. Ramp defines a delayed and accumulated response of output of a sudden change in input. A range is between specified upper and lower limits of a value or a device. Reliability is that the device will perform within the specifications for a number of operations for a time period. Reproducibility, similarity of one measurement to another over time, where your operating conditions have varied within the time span, but the input is restored. Resolution, that's the smallest interval that can be identified as a measurement varies. Resonance, that is the frequency of the oscillation, and that's maintained due to natural dynamics of the system. Self-heating, that's the internal heating caused by a device due to electrical excitation. Sensitivity, that will define how much the output changes for a specified change in input. Set point, that's used for closed loop control, and you want it to operate at a certain set point. Span adjustment, difference between maximum and minimum range values. Steady state is where the closed loop control, where the process no longer oscillates, but it has reached a steady state point. Stiction, it's a shortened form of static friction, and that's defined as a resistance to motion. Stiffness is a measure of the force required to cause a deflection. Thermal shock is abrupt temperature change applied to an object or a device. Sometimes if we want to do accelerated tests to determine how long the device will last, then we also use something like a thermal shock. Time constant is the time taken for the output to reach 63.2% of total change when we have a stepped input again. transducer is an element or device that converts information from one form to another. So we use transducers to measure things like temperature, level, flow. Transient is a sudden change in a variable, which is neither control response nor long lasting. So it goes past and then it will go to the original state. Transmitter is then a device that converts one form of energy to another, and mechanically to electrically. The variable is some quantity of the system or the process. We have measured variable and controlled variable. So we'll measure a certain variable, and then we might want to control it at a certain level or flow. Vibration, that again is motion mechanically or oscillation of an object. And zero adjustment, it's in an instrument, it's output provided when no or zero input is applied. In looking at process and instrumentation symbols, so there is a first letter and second letter. So the first A would be for analysis, second one will be for alarm. So that is symbols that we use in process and instrumentation diagram. Okay, Alex, it seems like you have an up and down. Did you just join us, or do you have a bit of a problem with your internet connection? So there's a picture of an overall control system. So there's the set point that we have referred to just now. We have a certain input element. Okay, but glad you're back with us, Alex. So you can see that gives input to the controller. There's the transducer that we talked about. And the example over here is an RTD. So that will then give a certain input, which will be compared to the set point. That will generate input for the controller. And then we must have some sort of final control element. For this example, let's say it's a valve. There might be some disturbance variable as well in the process, and then that's applied to the process. And then we measure to make sure that whatever our input, that is we have reached the level that we wanted from the set point. So you can see this point over here is the manipulated variable, and there's the feedback variable. And there's the controlled variable, the process variable. So just to look at the definitions. So this two blocks makes up the loop controller. Okay, and in this loop controller, we will also do our compensation to make sure that we have a stable closed loop system. Now moving over to temperature measurements, there's two main types of temperature measurements. One is contact, so it must be in contact with what you ever want to measure, the fluid or whatever you want to measure temperature from. And then we have non-contact. So on the contact side, we have things like thermocouples, RTDs, thermistors, and they vary in electrical resistance or changes in temperature. The non-contact is things like infrared, so that's used a lot to pick up any hotspots, or it can also be acoustic. So that don't have to be in contact with the medium that you like to test. There's a few pictures of temperature measurements. So what wasn't mentioned in the previous slide is the mechanical temperature sensor, which can work on the principle of expansion of a fluid up in a capillary tube. And on the right hand side we have RTDs. You can see there's two types. There's a thin film RTD element at the bottom and wire wound on the top. And then we have our thermistor, and then lastly the thermocouple. So as you can see, all of this falls within the contact types of temperature measurements. So looking at the thermocouple, so it's two wires of dissimilar metals that are then electrically connected at one end. That's the measurement, or the measurement junction, and then firmly connected at the other end, which is then the reference junction. So there's the reference junction. So what happens is that if those two metals are exposed to the same temperature, there will be a voltage difference, and that voltage difference will then tell us what is the temperature. Then we have resistance temperature detectors, and they are made of pure or lightly doped metal. The resistance increases with increasing temperature, so it's a positive resistance temperature coefficient if the temperature increase or the resistance increase with temperature. So most of these devices are either wire wound or metal film. So that's the one device that sorry, it's the wrong way around. When I go back to the picture, so there's our RTDs, the thin film at the bottom and the wire wound on top of it. So you can see an actual picture, and there's then the picture of the thermocouple, which we've just looked at. So in the most popular RTD is the platinum film PT100 with a nominal resistance of 100 ohm plus minus 0.1 ohm at 0 degrees Celsius. And then the last one that we had a picture from is Thermistors. That's a cheap form of temperature sensing provided by the thermistor, which is thermally sensitive semiconductor formed from oxides of various metals. Now, their accuracy is typically 10 times better than the thermocouples, but not as accurate as the RTDs. So it's non-linear devices, and we can use it between minus 80 and 250 degrees Celsius. And just to go back, again, not to the front, but to the back. So go back to the picture. So there's your thermistor at the bottom of that picture. Okay, so the temperature in the RTD device is measured in terms of A, potential difference, B, resistance, C, voltage, or D, current. Okay, so Jeffrey says it must be B. Okay, so if you think about what we've just discussed, the RTD, it is resistance, so that is the second one.